Welcome to the Legion Strength and Conditioning Podcast. You can check us out at legionsc.com or follow us on Instagram at legion.sc. All right, we have a new segment. I don't know if segment is the right word. A new episode format for the Legion podcast this week. This is going to be Science with Sergio, episode number 1. We have Sergio Paserno on the podcast today. And Sergio is a coach in Chicago, coaches at PXM, Powered by Movement, as well as Lincoln Park CrossFit. And Sergio is the type of person who will read a variety of scientific papers related to metabolism for fun, which is an admirable trait and quality. And, send me emails about them, and we'll talk about this stuff a little bit, and figured it might actually be something that would be interesting, not just to us, but to potentially the broader community and some folks who listen to this podcast who do have that tendency to want to know the ins and outs of whatever lactate, pyruvate, acetyl-CoA, all those great compounds. But we're going to actually talk about a paper today from Iñigo San-Milán and actually break down some of the interesting facets of metabolism that paper exposes, and hopefully give some useful application to folks who are training or competing or coaching in the sport of fitness, as it were. So Sergio, welcome to Science with Sergio, your own show. What paper are we actually talking about today? What's going on?
So today we'll be reviewing, so it's called the assessment of metabolic flexibility by means of measuring blood lactate, fat, and carbohydrate oxidation responses to exercise in professional endurance athletes and less fit individuals.
And we'll link to this as well in case you also would prefer to, sit down and read a relatively dense paper in your free time.
For sure. Yeah, it's a really good study. It basically analyzes the relationship between blood lactate, fat, and carbohydrate oxidation. So basically substrate catabolism, the breakdown of carbohydrates and fats in skeletal muscle tissue, and kind of the differences that we see there in professional athletes, and then like normal people, and then a sick population, and a population that we classify as people with like metabolic syndrome, so heart disease, type 2 diabetes, that kind of thing, right?
Yeah, totally. And the actual sort of point of the study is to come up with a way to sort of measure like substrate utilization in metabolism, right? So whether people are predominantly metabolizing fat or carbohydrate. And the goal was to sort of show the relationship with blood lactate levels and sort of metabolic substrate utilization, which I actually think is one of the least interesting parts of the study. They do succeed in showing that, but I think that the more interesting stuff is a lot to do with the actual mechanics of metabolism and some of the lactate utilization that they show, which is, probably pretty relevant for a fitness population. So I guess before we really start breaking down the specifics of this study, it's probably useful to give folks just kind of like a baseline understanding of some of the metabolic concepts that we're going to be talking about. So again, we're using a lot of words that people have probably heard or seen or, reviewed in some various coaching certifications like lactate, metabolism, anaerobic, aerobic, what's is lactic acid related to this, all that kind of stuff. So to start with, maybe we should give like a brief outline of the important metabolic concepts that we're going to be talking about. So Sergio, what do you think people should know?
For sure. So in the title, like it's obviously called the assessment of metabolic flexibility. So defining metabolic flexibility, it basically describes the ability of an organism to respond or adapt according to changes based on metabolic demand. So originally it was used to kind of describe how parasites generate chemical energy in specific metabolites aerobically or anaerobically. They're very versatile with that, and they have a very high metabolic flexibility. And so in turn, their ability to respond and adapt to changes in their environment is very high because they're able to switch very easily between fat oxidation and carbohydrate oxidation. So the utilization of fat and carbohydrates is their ability to catabolize those and convert those substrates into energy is very high. So they have a very high metabolic flexibility. So in turn, a group with low metabolic inflexibility displays a poor ability to oxidize fat or break down and utilize fat. They rely primarily on carbohydrates. And I think it's important to understand that. So lactate is a byproduct of a couple metabolic pathways. So in cellular respiration, glycolysis is the process upon which glucose is catabolized in the cytosol. It doesn't require oxygen, and pyruvate and lactate are the end products of that metabolic pathway. And then so at the end of glycolysis, we're left with some NADH and some ATP. And then from there, pyruvate is then shuttled into pyruvate oxidation, which basically takes pyruvate molecules, breaks them down into acetyl-CoA, which is super important for the Krebs or the citric acid cycle. And then so from there, the TCA occurs in the mitochondrial matrix. The TCA produces a few molecules of NADH, one molecule of FADH2, a little bit of ATP. And then from there, that NADH and FADH basically catalyzes the rest of cellular respiration, which is the electron transfer chain. And that's how we get ATP from like glycolysis, cellular respiration, and the breakdown of glucose there without oxygen. And then in, sorry, I lost what I thought.
No, yeah. So let me kind of zoom out a little bit, right? So all those terms that were just being thrown around, if anyone ever took, a chemistry class or certain biology classes, you probably had to do some things where you memorize certain aspects of the Krebs cycle, et cetera. And you're like, okay, I vaguely remember that this is a thing. And essentially I think the key points to really home in on are that the energy that we actually use to do everything we do, comes from ATP, right? So this is an important molecule in the body, and there's a lot of ways that the body sort of generates ATP, essentially from ADP, which is, it essentially just adds a phosphate group to a previous ATP molecule that has lost its phosphate group. So this is not necessarily the easiest thing to sort of hear and understand, but like everything we're doing, whether it's metabolizing fat, carbohydrate, whether it's, shuttling lactate around, whether it's performing aerobic metabolism or anaerobic metabolism, we're trying to just make more ADP or ATP to be able to do more, muscle contractions or whatever we're trying to accomplish, right? And if we sort of think about the different ways that this can occur, we have a few different trade-offs that are happening, right? So if we are trying to get the most ATP per sort of like reaction, the way that we do that is aerobically, right? Is that we actually aerobically metabolize fat, and that creates the most ATP per reaction. However, that's a little bit slower than anaerobic metabolism, where we're not actually oxidizing, we're fermenting sugars, right? And that's a faster reaction, but it's less efficient. And then it also creates more metabolic byproducts. So if we think about what's actually happening if we're exercising at high intensity, we're often outpacing our ability to create ATP, and we're having to switch to less efficient forms of metabolism in order to keep moving, right? And those less efficient forms of metabolism produce more byproducts that can potentially cause metabolic problems for us. So, that's sort of like a big picture idea of what's happening. And people may have heard some of these concepts before in terms of like the fat burning zone or whatever when doing cardio, which is really just kind of like a almost purposeful misapplication of what's going on here to confuse people and try to sell them something that they don't need. But in reality, as you mentioned about metabolic flexibility, people who are good athletes are just constantly switching back and forth between these different forms of metabolism based upon the amount of ATP that's required, the speed that they need that ATP, and the fuel substrates that are potentially available to them, right? So that's kind of like what the conceptual framework is for what we're talking about. Sergio, did I say anything that's incorrect or needs clarification in there?
No, for sure. And I think you touched on that really well. And you kind of talked about the idea of aerobic and anaerobic processes. And I think it is important to understand that like we shouldn't necessarily think of either of those as with or without oxygen, because I think that's the general conception is like one is with oxygen, one is without oxygen, right? So generally those are always occurring in the presence of oxygen. It's just, it really comes down to the speed at which the muscle is demanding ATP, right? So like you said, aerobic simply means you're generating ATP at a rate in which all of the energetic demands can be met by mitochondrial oxidation, right? That kind of like breakdown of fats, utilizing oxygen. And then anaerobic just basically means that the demand for ATP has now exceeded the capacity of that mitochondrial oxidation. And so you kind of just switch back and forth from those.
Yeah. And like you said, both of those are occurring all the time, right? Like at any given moment, your body and your cells are creating energy both aerobically and anaerobically. And the distribution of how much energy is being created through each of those mechanisms is just kind of switching, again, based upon the demands to the specific area that's working, as well as the fuel substrate that's available, right? So it's not like, oh, all of a sudden the switch flips and now I'm quote unquote anaerobic, right? It's like you're always doing both.
For sure. And I said, and you touched on kind of how switching between which the tissue that's working at primarily. So it's like touching on that, like the difference in fast twitch and slow twitch is pretty correlated to that aerobic anaerobic response. So like oftentimes it's pretty understood that fast twitch and slow twitch muscle fibers twitch at different speeds, but in reality they twitch with a different force. And kind of the speed there is we can look at that as how quickly each of the types of fiber fatigues, right? So slow twitch muscle fibers are simply less of a forceful fiber than type 2A and B, right? So type 2A and B have just more motor endpoints, and they
and by type 2 you mean fast twitch muscle fibers.
Yeah. Sorry about that. And so they generate a little bit more force, but that trade-off is they require more energy, and in turn they fatigue much faster, right? So the type 1 fibers are just way more efficient at producing energy. So therefore the overall metabolic stress and energy requirements is going to be way lower when you're primarily utilizing those slow twitch or oxidative muscle fibers, right?
Yeah, totally. So the idea of fast twitch and slow twitch is probably a little bit relevant for this specific study, and just a general concept that's kind of out there in the community that people may not have, a super clear grasp on. And then I think the other thing that's important, we've been talking about lactate a bunch, but there still kind of persists this idea that lactate or quote unquote lactic acid is a bad thing, right? That, if you're accumulating lactate or lactic acid, in the blood while exercising, that's either, the cause of fatigue, right? It's like, my legs are turning into lead. That's lactic acid. Or, the next day I'm sore. It's the lactic acid that's in my bloodstream that's causing the soreness. And I think that, the contemporary understanding is that neither of those are really correct to varying degrees of incorrectness. So can you give us maybe just like a brief summary of what the role of lactate actually is in physiology for people who are exercising?
Sure. And so this is where shit starts to get a little complicated. I think there's, and I won't really get into this study, but there was a really good study titled Lactate Transport in Skeletal Muscle, Role and Regulation of Monocarboxylate Transporters. So there's this relatively recent discovery of MCT, and MCTs are proton-linked monocarboxylate transporters. Essentially what they do is they're responsible for the flux, so the efflux and the influx of lactate and hydrogen in and out of skeletal tissue. And so those are a couple mechanisms in which are metabolic pathways in which lactate is cycled into tissue and then out of tissue, and those are super important for maintaining that homeostasis within like the slow twitch muscle fibers. And I think oftentimes when people talk about that like lactate threshold, right, they're talking about that point at which there's a significant there's a point at which there's a significant accumulation of lactate in the muscle tissue. And
yeah, totally. So it might be useful to sort of think about, lactate is being created, and then people have this idea that it's like a bad thing. Right. So like what is actually happening with lactate might be like a useful way to think about it or to explain it, right? Where it's like, this is being created and it's being spit out, and then it's accumulating and it's being used up. Like, how should we think about that?
All right. So the trade-off there is that like the fast twitch muscle fibers and kind of like the when you are utilizing carbohydrates primarily as an energy source, lactate is a byproduct of that cytosolic catabolism of glucose, right? And then like you said, like generally lactate is thought of as like a waste product. when in reality it's just a byproduct, and it's actually like a really, really important fuel. So there's a couple concepts upon which aren't fully understood, where lactate is shuttled into skeletal muscle tissue, specifically slow twitch oxidative fibers, and there's this oxidation of the lactate occurring in the mitochondria of those muscle fibers, and then from there that lactate is being recycled and turned over into basically acetyl-CoA and pyruvate, and then that's in turn able to be reutilized as energy. So at that point, the lactate.
Yeah, and to interrupt quickly, right? I mean, pyruvate and acetyl-CoA are some of the key compounds that are actually dumped into, metabolic reactions, right? That a lot of what the body is doing in metabolism is converting the protein, the carbohydrates, and the fat that we eat or potentially store in our body, as muscle or glycogen or whatever, into pyruvate and acetyl-CoA to actually metabolize those to create ATP, right? So those are kind of like the key compounds that almost everything gets turned into in order to be metabolized. Sorry, go on.
No, and you're right. So I think and again, like that, those mechanisms upon which lactate is being oxidized and broken down and reutilized in the mitochondria isn't fully understood. But I think it's the important aspect there is that that's occurring in the mitochondria. And so like the function of the mitochondria and increasing function of the mitochondria, there's a direct correlation between the ability to reutilize and recycle that lactate. And so the study essentially emphasizes how the professional athletes basically have the most elite functioning mitochondria, and that's why they're so efficient at then in turn taking that lactate and actually being able to maintain it and contain those levels within muscle tissue and not particularly have to excrete excess lactate into the blood, because the function of the mitochondria, the density is so high within the mitochondria of the slow twitch muscle fibers.
Yeah, totally. So if we're starting to jump into the actual study at hand, right, there's 3 groups that were essentially, put on an ergometer, some sort of cycling ergometer, and asked to do. I actually don't remember the structure of the test they were doing. What was it? Was it just like a standard VO2 max test, or how did they do it?
Yeah, so it was just a standard cycle ergometer test. I think they were put on it for, I believe it was 10 minutes. And basically what they were doing is they were trying to very gradually increase the wattage until they started to see that accumulation of lactate in the blood. And they were measuring at which point that was starting to occur relative to fat oxidation and carbohydrate oxidation in the 3 groups.
Yeah, totally. So just to give a brief summary of the paper, there were 3 groups, right? One, as you mentioned, is actual professional cyclists, right? So people who are at, the top tier. I think they had to participate in whatever the top tier professional cycling organization is, right? So, I mean, this is the equivalent of someone being an NBA player or like playing soccer in La Liga or something where it's like best of the best, right? Then there was a moderately active group, which was people who exercise, but, are not by any means professional athletes. And then there was a group that actually had, metabolic dysfunction. I don't know if they had to be diabetic or if they had to sort of fail some sort of glucose tolerance test or what exactly they used to categorize them as that. But those were the 3 groups. And they were essentially, like you mentioned, measuring their respiratory exchange, which is kind of a classic way to figure out how much, carbohydrate is being metabolized versus how much fat is being metabolized. And then they were simultaneously pricking their earlobe, which I thought was pretty funny. If you've ever done like a lactate test on your fingers, it sucks. It's not a pleasant thing to have done, where you're just like, dying on a bike or whatever and like having your finger poked every 2 minutes, and you're like, I hate this more than anything. I don't know if the earlobe would be any better or worse, but they were pricking their earlobe to measure their blood lactate levels, right? So this is sort of the study design, and what came out of that, like you mentioned, is that the professional athletes are simultaneously creating a lot more lactate, right? It's not like they're producing less lactate. They're actually producing more than the other groups, but their mitochondria are so efficient and so essentially powerful, I don't know if that's exactly the right word, that the mitochondria are able to then immediately reutilize this lactate as fuel to continue exercise at a rate that was much, much higher than the other groups.
Yeah, 100%. And I think that's where a lot of that's where this study gets really crazy, is that when you're looking at, and I guess I can give a little context to blood lactate levels at rest. So, and I guess this could expand a little bit on the significance of lactate. And so lactate is always in our blood. It's always circulating throughout the body. And that isn't necessarily fully understood. It could potentially be a signaling molecule. Based on the current research, it's not fully understood. But for context, so about an average blood lactate level for a normal individual, and so interesting thing about that was the way they characterized normal functioning individuals, moderately active individuals, was we're exercising about 3 times a week for, I think it was about a total of 3 hours, which is still a pretty significant amount of exercise. And so we can refer later to the type of exercise that they were doing, but like even the moderately active individuals are characterized by doing a significant amount of exercise relative to, I think, what like a general population would assume. So those individuals at rest have about 1 millimole of lactate per liter of blood. The professional athletes at rest sit somewhere between 0.5 to about 1, generally around the 0.7 range, so kind of like right in the middle at rest. And then the group with the metabolic syndrome, so the like the insulin resistant group, the people with type 2 diabetes, cardiovascular disease, and all that, have an average blood lactate level at rest of 2 millimoles, right? And so for reference, I don't know if you've ever been on a watt bike or done like a VO2 max test, but essentially the professional athletes didn't get to about 2 millimoles of lactate until they were somewhere around expressing somewhere around 250 to 300 watts of power output. So for reference, their body is so efficient at utilizing fat and oxidizing fat that that correlation between fat oxidation and blood lactate levels was, so they're able to primarily utilize fat, pull in lactate into the mitochondria of the skeletal muscle, recycle that, and they don't necessarily need to pump that lactate into the blood. Whereas the kind of the sick group never is really able to utilize that fat effectively. So they're constantly relying on that kind of like that carbohydrate or glucose catabolism for the production of the ATP. And that results in a lot of lactate being pumped out continuously into the blood. And that's how they were kind of able to see that pretty strong inverse correlation between blood lactate levels and fat oxidation, right? So basically the inability to utilize fat because of mitochondrial dysfunction basically means that you're just going to be pumping out way more lactate into the blood than if your mitochondrial function was way higher.
Yeah, totally. And to kind of summarize that related to some of the points that we made earlier, the elite athletes are able to utilize, aerobic metabolism of fat longer and to create more power than non-elite athletes, right? Which is what we would expect. As we mentioned before, the aerobic metabolism of fat is the most efficient in terms of creating the most molecules of ATP per reaction of the ways that we can actually, metabolize anything. We get the most molecules of ATP per reaction with aerobic metabolism of fat, but it's the slowest, right? We get the actual slowest turnover of ATP through that reaction. So like we said before, if you're in a situation where your working muscle is running out of energy, you need to use more anaerobic metabolism to supply ATP, even though you're getting less per reaction. Whereas if you're able to maintain this aerobic metabolism of fat longer, you're able to maintain a more efficient utilization of the substrates that you have available, right? So that's pretty much exactly what we would expect is like, the people who are better athletes can maintain a more efficient mode, quote unquote, of metabolism at higher power outputs than people who are not. And something that might be a little bit tricky that you started to touch on a little bit is that people who are in this metabolic dysfunction group actually produce a lot more lactate, not necessarily produce more lactate, but have higher blood lactate levels because they're essentially relying on anaerobic metabolism in order to do much lower power output activities because they do not have the metabolic machinery that enables them to utilize, the more efficient form of metabolism to do those lower power output activities. Is that like a reasonable way of summarizing that?
No, definitely. And I think something to kind of highlight with that is generally there might be this assumption that like elite athletes are producing less lactate, and when in reality, they're actually capable of producing producing way higher levels of overall lactate, but their skeletal, the red muscle fibers, the oxidative fibers, are so efficient at taking that lactate, oxidizing it, recycling it, and reusing it for energy that it doesn't have to be accumulated or coagulated in the bloodstream, because it doesn't have to be excreted from the muscle tissue, right? So the gift of like elite athletes potentially isn't their ability to produce less lactate. It's the mitochondria's ability to kind of take that lactate, recycle it, and reutilize it.
Yeah, something that might be helpful to think about, and I'm not sure if this is actually correct, but I'm just kind of trying to model this in my head and explain it in a way that might be useful, is that, you know, my model for this is that elite athletes are essentially just like doing more of everything, and they're doing it better, right? So it's like they're doing more aerobic metabolism of fat, and they're simultaneously doing more anaerobic metabolism of carbohydrate, right, than someone who's not elite. They're just producing a lot more ATP in general. And then they're also better utilizing the byproducts of that anaerobic metabolism than the people who are producing less. So it's almost like if you use like a, maybe like a financial analogy might be helpful here, right? Where they're the equivalent of a business that has a lot of cash flow in a lot of different areas, right? So it's like they're taking in a lot of revenue. They're also spending a lot of money on advertising and staff, right? And they have all these accounts with a lot of money coming in and coming out everywhere at the same time. Whereas someone who's, you know, less metabolically healthy is essentially just like spending a lot of money without taking in a lot of money. I don't know if that analogy breaks down in a lot of ways, but that might be like a somewhat useful way to conceptualize it. I don't know.
No, that absolutely makes a lot of sense. And I think it's actually really ironic because like the elite athletes are so efficient at storing and utilizing glucose, even though they really don't rely on it, that they're able to store like 2 to 3 times the amount of glucose in a cell than like a normal or sick individual. And they're not even using it, so they don't even need it. So I think, yeah, there's definitely a lot of truth to that.
Yeah, totally. So if we start to think about, okay, we have these different groups, we see this result where the elite athletes are producing and utilizing more lactate. So their blood lactate levels actually stay lower longer until they get to certain levels of power output. And then the sub-elite groups, you know, the moderately active athletes, you know, they see like a gradual rise in blood lactate, you know, that peaks earlier than the elite athletes. And then the metabolically dysfunctional people, you know, their blood lactate is high to begin with and then gets higher right away. And then they, you know, sort of fall apart and aren't able to even hit the higher power outputs. You know, the actual point of the study was to sort of correlate this with fat oxidation. So they could see what is the relationship between blood lactate level and fat oxidation. So what did they actually find with that?
Sure. So there's that like very, very strong inverse correlation between the ability to oxidize fat and levels of blood lactate, right? So basically, the more efficient you are at utilizing fat or lipocytes as your primary energy source, the less you have to rely on that carbohydrate metabolism. As a result, less blood lactate is pumped into the blood, and so it doesn't coagulate, right? So I guess why that would potentially be a good thing is there's that association between lactate and a decrease in performance or fatigue. So there's a few like central or peripheral mechanisms that actually cause lactate to make that makes lactate in which lactate makes it more difficult to continue to do exercise. And those aren't fully understood. There, it could have to do with lactates kind of acts as a blocker in your muscle's ability to contract. There's an increase in blood lactate means an increase in hydrogen, and the hydrogen ions bind to kind of pain receptors or neural cells and kind of signal that you're in a significant amount of pain. So that could signal you to kind of stop.
So if we think about the actual results of the study, right? What was trying to be shown is a correlation between blood lactate levels and fat oxidation. And what was shown was that there's a strong inverse correlation between these, right? That as blood lactate concentration goes up, fat oxidation goes down. And this is, again, measured by pricking people's earlobes to see blood lactate concentration. And then they have the actual gas exchange thing that's sort of measuring their respiration and showing how much fat is actually being oxidized as they go. So as blood lactate levels go up, fat oxidation goes down. And then there's a lot of potential things that could be going on here. I mean, we have some ideas about different fatigue mechanisms that lactate either causes or is correlated with. And we also have this idea of like, okay, there's sort of a constant flux of metabolism between these different modes, right? We've talked about aerobic metabolism, anaerobic metabolism, different substrates, et cetera. And it's also possible that, lactate is potentially displacing fat in some of those pieces as well. So, there's a few different possibilities there. And I think they touched on a few different things. What do you think is actually going on that's causing this negative correlation between blood lactate levels and aerobic metabolism of fat?
For sure. So one thing that we do kind of know is that lactatemia is like this very gradual increase of lactate in the blood. And that's associated with the downregulation of lipolysis, which is essentially the breakdown of fats. So with the accumulation of lactate or excess lactate, there is some mechanism occurring that forces the body to downregulate or makes it more difficult to in turn oxidize fat. So basically just because fat utilization starts to decrease because of the increase in blood lactate, it just ends up making that a lot more difficult.
Yeah, and I think it's worth mentioning, and this was like almost a throwaway line or two in the paper where I was like, this is actually super interesting and I'm curious about this. It seems like increased lactate concentration potentially both inhibits lipolysis, so actually breaking down the fat in order for it to be metabolized, as well as the actual oxidation of fat, right? And those are separate steps. So the fat has to be set up to be metabolized, and then it actually has to be metabolized. It seems like lactate may actually inhibit both of those. Although I think they mentioned that they have some research in mice, but I'm not sure if there's actual human studies on that.
Yeah, there's not a lot of certainty with that, and they're just kind of like throwing that out there. But that's the mechanism in which they think the increase in lactate is correlated to the decrease in fat oxidation.
Yeah, totally. So basically, as blood lactate levels accumulate, the various steps of fat oxidation potentially get inhibited by the lactate itself, right? So, we mentioned previously that lactate isn't necessarily the bad guy that people make it out to be, right? That it's not the cause of soreness and it's not the cause of fatigue, right? That lactate is actually a preferred fuel of working skeletal muscle and also the brain and the heart, right? So we're actually very, very good at utilizing lactate. However, once concentrations get to a certain point, we potentially start to kick off a bunch of feedback loops that do inhibit other aspects of metabolism or potentially cause certain fatigue mechanisms to kick in.
For sure. So I think that's where, because lactate is primarily a signaling molecule, and I think that's the hypothesis in that, like, lactate actually doesn't really make you tired, right? Like, lactate signals, when it's pumped into the blood, it signals for more hydrogen ions to be pumped out into the blood, and then there's some correlation between hydrogen ions and fatigue and the difficult ability to contract muscle fiber, or just like it binds to pain receptors, and it kind of tells your body that, like, hey, you're in a little bit more pain, there's something wrong. But lactate through MCTs is pumped to pretty much every cell in the body. It can be uptaken by the brain, it can be utilized by the heart, it can be found in lung tissue. And actually, it could potentially be argued that lactate is one of the more important energy substrates in the body. There's this hypothesis that lactate is actually the preferred fuel source for the brain in patients with traumatic brain injury, mainly because lactate is such a quick fuel source, and that potentially has to do with lactate's ability to bind with beta hydroxybutyrate in the brain. But just like new studies are continuing to find how lactate can be uptaken by cardiac tissue or the heart, and it's used as a respiratory substrate. It can be broken down and utilized as energy there. So it actually is really essential to the function of many different cells, and I think we're starting to see that more now than we did before.
Yeah, so we have kind of a complicated picture of what happens as blood lactate levels start to rise, right? There's sort of the classic correlation is not causation situation where, in the past we saw, high blood lactate levels correlate with soreness, high blood lactate levels correlate with fatigue. And the assumption was that lactate was actually causing these things. But in reality, lactate is going to be a byproduct of anaerobic metabolism, which is indicative of a workout being hard. And then there's a bunch of other things associated with hard workouts like soreness. And there's also a bunch of other potential like fatigue mechanisms and potential, metabolic substrates, et cetera, that are actually causing more of the problems. And it's not necessarily lactate's fault, right? So that's kind of like an updated view of the kind of, 70s running wisdom surrounding lactate. But simultaneously, there are some potential things that we're sort of touching on here where lactate does have the capacity to inhibit, mitochondrial oxidation of fat. So it's like, okay, lactate isn't the bad guy that people thought it was, in the sort of like 70s jogging lore. But that said, there is some potential for it to actually inhibit, our whatever more efficient forms of metabolism. So we have this study and we have these ideas about metabolism, and we're trying to, redefine lactate's role in the public eye. And that's all, again, hopefully interesting for folks listening. But there's also an element of like, okay, I want to get better at CrossFit. I want to do well in the open. I want to be fitter. I don't really like, what does this actually mean for me, right? So, there's potentially a few different ways that we can try to break down the potential practical takeaways from this. So Sergio, what do you think are the important concepts for someone who is trying to coach someone to perform better in the gym, or for someone who themselves is trying to perform better in the gym?
For sure. So when considering, like we touched on kind of like how lactate might contribute to fatigue or specific like substrate utilization, and so that can kind of apply to athletes in a lot of ways. I think one of the main emphasis of the study was improving the function of the mitochondria in an effort to hopefully effectively be able to recycle lactate more effectively. And so I guess there's a couple ways to do that. And generally, so there's this idea that you should do more like long, steady state cardio. And that was something that I heard a lot, and I never really understood why or what was kind of happening in the body when you're doing that, right? And I think that can be kind of defined as that like zone 2 training, or that like conversation pace training. And basically what that is. In zone
2, you're referring to heart rate, right? Can you just maybe give like a brief explanation of what that means?
Yeah, sure. So there's, I guess a lot of people define training zones very differently. Iñigo, he obviously wrote the study, defines 6 training zones. And so zone 2, he defines as basically the zone in which you're producing your maximum aerobic output. It's the zone where the slow twitch muscle fibers are being maximally stimulated, right? So it's basically like your it's your zone where your fat max sits. So it's basically the exercise intensity where you're primarily oxidizing fat and the most fat possible, right? So that would be something like sitting on a bike for 60 minutes at a conversation pace, right? So if you don't have an ability to measure your blood lactate levels, it would be kind of that like 65% of your maximal heart rate, something like that.
Yeah, and in terms of like a rate of perceived exertion, especially for a CrossFitter, right, this is going to seem easy. Right. It's like, it's not necessarily walking, but it's not hard. Because I know that this is something that people try to potentially do where they're like, oh yeah, I'll add in some, additional zone 2 aerobic work, or I'll add in some cyclical work to kind of like improve my engine. And then because they're CrossFitters, they actually end up going too hard, right? Where they're like, okay, cool, I'm going to ride my bike erg, that's in my spare bedroom for 45 minutes. And I'm going to try to beat my previous 45-minute distance on that. And it's like, no, that's too hard. Like, this should be, again, conversational, I think, is a good way to do it, where it's like you're potentially breathing and it's not necessarily like an easy walk in the park type of thing, but it's not like you're having to focus and push the intensity at all.
No, for sure. And you're right about people generally are going to exceed that capacity or kind of like try to push the needle with the zones that they're training, right? So it's like there's this
especially if they're not good at it, right? Especially a lot of like intensity junkies who don't necessarily have this capacity for this like impressive, fat oxidation power output coupling that we've seen from these elite athletes, right? Where it's like you have some people, especially within sports like CrossFit, who are very, very fit in some ways, but probably would not do particularly well on like a zone 2 power output test, right? That they flip over into like higher intensity zones of metabolism much more early.
For sure. And I think that's where also considering, so there's this saying where it's like people want to constantly test their endurance and they don't necessarily want to build it, right? So especially on the ergs, we have all these kind of mechanisms that tell us how much energy we're expending or how much power we're producing. So whether you're doing, like a lot of Metcons are 3 rounds, 30 calories on a bike for time or something like that, right? So it's like with chest to bars or snatch or something like that, you're constantly looking at your paces like, okay, I'm biking at 1250 calories per hour right now. So potentially when you're sitting on a bike erg for an hour and a half, you're thinking like, okay, I'm sitting right now at like 1,000 calories per hour. This individual would probably be here. So it probably means that like my capacity is pretty low. So I'm going to try to hold it at a little bit of a higher pace. And so that comparison of what potentially other people could be doing is going to start to influence how you consider your own performance on those pieces, right? So instead of saying like, okay, this is supposed to be a pace where I can maintain full control of my breath primarily in through my nose, I'm able to maintain a pretty decent conversation with my coach. Potentially something where you're not even looking at your monitor, people will generally start to consider what other people are doing and then start to kind of exceed that capacity because they think they need to meet that level, right? And I think the hard thing about that is when you look at like elite endurance athletes, for example, because this is the population that produce the most power output in these training zones, is like you could have somebody like an elite marathon runner running 7-minute miles, right? So for somebody who's able to hold 440 for 2 hours, like a 7-minute mile is pretty much a conversation pace, right? So you're kind of thinking like, well, okay, like what does a 7-minute mile feel for me? And it could probably feel like way different for a lot of people. That's like a maximal effort sprint. So having the ability to kind of say to yourself in the education to be like, okay, this is exactly what this is supposed to feel like. For me, that could be like a brisk walk pace. Like I could go for a brisk walk for an hour, whereas like an elite marathon runner would be running 7-minute miles. I think just like having that ability to know like this is what it's supposed to feel like. And I don't need to push that. There's no reason to kind of like move out of that training zone. And at that point, it's not going to continue to benefit you because you're just starting to kind of like compare to other people and get in your head about it.
Yeah, totally. And so if we're thinking about, okay, we want to apply this to, a more fitness-based athlete, and we're talking about this idea of zone 2 training to essentially build mitochondrial capacity, I also think it's important to note that this is not necessarily going to be something that results in like immediate performance gains for someone trying to do the open or whatever, right? Because if we think about the cyclists that were the elite athletes in this group, in a sport like cycling, the sort of let's say efficiency of your metabolic machinery is much more tightly coupled with your performance than it is in a sport like CrossFit, right? In a sport like cycling, it's just like, all right, straight up, we can do a math problem here. What is the average power output that you can maintain? And what is your body weight? Like, awesome. We can basically figure out who's going to win this race, and I think in something like CrossFit, you could probably try to reduce what's going on into a similar equation. But the reality is for a lot of people, the limiting factor is going to be more of like a local muscle endurance thing, especially for folks already at a reasonably high level, right? It's like my shoulders blew up, and that caused me to take a longer rest before kicking up into my next set of handstand push-ups, which is why I lost, right? Like I wasn't able to maintain the same cycle time on, moderately heavy power cleans where I had to drop the bar and rest 10 seconds, whereas, my competitor was resting 5 seconds. Or, I had to walk on my transition slowly, whereas my competitor rushed to actually pick up the rope and start double unders. So, the relationship there is a little bit different. And so simply improving this metabolic machinery, I think, is important for fitness athletes in a lot of ways. And I think it can improve their performance. And I think it can improve the quality of their training training. But for a lot of folks, especially who are already pretty good, I wouldn't necessarily tell them that this is going to be the limiting factor in terms of why they're not beating people or qualifying for something. What do you think?
No, 100%. And I think I'm thinking back to, and I can pull from a specific example is, for example, like yesterday, I had one of my athletes do a 17-minute AMRAP with wall balls, double unders, and deadlifts, right? And so it was just the rep scheme was 12 wall balls, 36 double unders, 2 deadlifts at 315, 225. So like a fairly heavy deadlift there. And in a more intense metabolic scenario is obviously going to feel a little bit heavier, but there's way more limitations that are going to present them in that scenario than just the function of the mitochondria, right? So that's like a super small part of your global performance in our sport, right? Because I was probably more concerned with the cycle time on the wall balls and the transition time between wall balls to the double unders back to the deadlifts, right? Even your ability to like unbuckle and buckle your belt, depending on the type of belt you have, like those things are probably going to have in the moment a much more profound effect on your performance. Whereas like stuff like this kind of like zone 2, improving mitochondrial density, like that mainly is just like we see stuff like improving your like the drainage of the lymph system, fuel substrate utilization, vascular density, like heart muscle efficiency, things like that will generally play more into your recovery as an athlete between sessions. Maybe potentially even like your mental state. Like I know for a fact I feel way better after I do like an hour row than I do like a 9-minute max effort metcon of thrusters and chest to bars. So the application of this is going to be a lot more specific to just kind of like your development as an athlete and as a human, as opposed to improving your capacity in the sport. And even then in cyclical elements, there's a lot more things that we have to consider. Was like professional cyclists are probably not going to be 210 pounds, 215 pounds, right? But oftentimes we see these people in CrossFit that are like 175 to 225 pounds on the men's side. And it's like, say, for example, somebody that's 205, right? Like they simply just, for the fact that they have more tissue and more muscle mass, their ability to produce output on a bike is going to be a little bit easier than somebody who is 175, right? Simply because of the fact that they have more tissue, right? So in that situation, like, is it beneficial to continue to improve that individual's ability, the individual that's a little bit heavier, that individual's ability to perform well on cyclical modalities, or do they have to spend a little bit more time focusing on kind of like the I guess for an athlete, like something that more of a limitation that will present for a larger athlete, right? So simply because they're a little bit heavier and they don't have to spend as much time building that system, because they already can produce enough power on the cyclical modalities to kind of like keep up or do what they need to in the sport, if that makes sense.
Yeah, totally. And I think that one of the points that you made in there is one of the more salient and important aspects of thinking about this, right? Because again, if we actually look at the data in the study, it's like these elite athletes were able to, maintain this power output in this cycling ergometer test with a blood lactate level that's extremely low, which means that they're able to train at that power output, using predominantly oxidative metabolism of fat. They're still pumping out a bunch of lactate like we talked about, but they're not necessarily hitting those accumulating levels of fatigue and other metabolic byproducts, potentially have downstream consequences for other training sessions. So in a sport like CrossFit, we do want to hit those points that are really, really challenging and are actually resulting in us kind of like pushing the limits and hitting a lot of those, nasty, disgusting fatigue elements. But if we can do a lot more training in a way that doesn't create as much systemic fatigue, then that enables us to do more training in general, which makes people better at the sport, right? So I think that in terms of how this is potentially applicable, especially for people who are looking to compete, it's that by improving your mitochondrial function, ideally, you are going to be able to do more training at a less, let's say, at a level that has fewer consequences on your overall systemic fatigue, which means that you get to do more training as a whole, which means you get a lot more reps in and everything becomes more sustainable, so that when you do actually have to push it, it's like you have this huge window that you're able to execute sustainably. And then there's still this little slice where it's like, okay, I know I have those extra gears if I need it.
For sure. And I think that idea right there can be applied to CrossFit in a lot of different ways. I think a pretty easy way to look at that for something like weightlifting is like, if you do a little bit more technique work, you'll be a little bit more efficient in certain scenarios. So you can accumulate a little bit more volume when you snatch, just because you're not putting yourself in harmful situations as frequently or something like that if your technique is a little bit better. So kind of like for aerobic or energy system training, you can kind of consider it like that, right? So because your body's the mitochondria's ability to kind of like take that, what would be considered like a negative waste product, that lactate, turn it over and utilize it efficiently, you're able to kind of do a little bit more in those higher intensity training zones and kind of recover from that, because the systems or the metabolic pathways that are responsible for doing that, for that recovery, are so efficient. Right. So it's like if, by doing a little bit more slower sustained work, you're able to touch on kind of like the intensity more frequently, in turn giving you more exposure to that style of training, which in turn is just going to give you more practice, a more accumulation of that type of volume than somebody else who isn't as efficient of recovering from something like that.
Yeah, totally. And there's probably one more thing that we should mention and potentially try to dispel up front, right? I mean, we're talking a lot about like burning fat versus burning sugar, quote unquote. And I think we mentioned this briefly, but it's important to note that this has basically nothing to do with actual weight loss, right? That the substrate that you are utilizing in order to perform an activity has very, very little to do with whether or not you are going to burn fat, meaning like reduce fat on your abdomen so people can see, the definition of your abs, right? That we use sort of like a financial analogy earlier. And, if we think about, again, these analogies are going to break down in certain ways, but what we're essentially talking about is like, okay, what is the actual flux of money in and out of different accounts? And what does that look like, as opposed to what is the balance within the account, right? Because everyone sort of knows you can have someone who makes a lot of money and spends a lot of money, and their account balance is actually, that's actually a bad analogy. Scrap that one. We're going to try a different one, because we want like the valence of the specific thing that we're talking about to sort of correlate. So let's say you have someone who has a credit card, and they put a lot of stuff on their credit card all the time, but then they pay it all off. Right? That's sort of like, they can put a lot of money on their credit card, but they have enough money that they can pay it all off. And then that's not necessarily a problem for them. However, someone who is accumulating a lot of credit card debt by putting a lot of stuff on their credit card and not paying it off, that's sort of like the equivalent of what we're talking about with metabolism here, right? That you can actually burn a lot of fat in your exercise, but it doesn't necessarily matter, because we're just talking about like what the flux is between accounts, not what the actual balance is on someone's credit card, which would be, in this case, the amount of body fat that they have stored. I think that was kind of circuitous and not necessarily totally helpful, but I wanted to make sure that people didn't get the wrong idea about like, oh, I'm going to burn fat.
No, for sure. And I think what you're saying with that, and that was actually a pretty good analogy. So kind of what you're saying is people, both types of people can accumulate that credit card debt. Or just like that
credit card balance.
Yeah, credit card balance, right? And so basically, but what the difference there is their ability to pay that off, right? And I think there's a pretty specific example to that, which I don't want to go too deep into, but basically there's this thing where there's this mechanism that we see in people with type 2 diabetes and professional athletes. And these are the only two populations that we see this in. But outside of the mitochondria exists this reservoir that actually holds fat, right, or like fat cells. And so in the professional athletes, those those reservoirs of fat, the fat is actually active. So I think it's 25 to 30% of total fat oxidation, or the fat being oxidized, is taken from those reservoirs. So basically because it takes so long for fat to be kind of like transported into the mitochondria to be utilized as, or broken down and utilized as energy. Well, basically the professional athletes developed these reservoirs right outside of the mitochondria that were very easy to store and just pull fat from. Right. So it's like very readily available fat. And we see the same thing in people with type 2 diabetes, but in the population of people with type 2 diabetes, that fat is inactive and it simply just accumulates. Right.
Yeah, totally. So professional athletes have like finely marbled muscle tissue, just the same way that a cow being fattened for the slaughter does, right? It's basically what we're saying. All right, cool. So Science with Sergio, episode 1. We talked about a lot of different stuff, was reasonably technical, tried to, not shy away from the science and the technical terms, but hopefully make it somewhat accessible. If this was helpful, please let us know. We always want reviews or whatever, but you can email me directly. If you're on the Legion newsletter, you get my emails periodically. So follow up and let me know if this is actually useful. Sergio, any sort of parting thoughts on metabolism?
No. So, basically we don't want to see lactate as a negative thing, right? It's not a waste product, it's a byproduct. And it actually contributes very positively to a lot of mechanical pathways. And it's super important for understanding how our body is able to break down substrate. And even so, the medical application of this study is that we're able to effectively see kind of like if people are experiencing mitochondrial dysfunction based on whether or not they're primarily utilizing fat or carbohydrate, and by looking at as the primary source of energy, and by looking at the levels of blood lactate.
Yeah, totally. And maybe we can all just like start pricking our earlobes while we're trying to do thrusters and pull-ups and see what the hell's going on.
I think that'd be pretty good for client retention. I think people would like that.
Yeah, sounds terrible. Sounds like me getting my ears pierced at Claire's. Thanks for listening. While you're here, go ahead and head over to your podcast player, subscribe to the show, give it a rating, give it a review, all that good stuff. You can also go ahead and click through to the show notes where you can find out more about us at legionsc.com, and also follow us on Instagram at legion.sc.